Welcome to my presentation on data pipelines in ICESpark. My name is Joshua Yuan, and I've been working under the direction of Dr. Jiao Yu this summer. To start us off, we must first understand where the issue we are trying to tackle lays. As many of us have been made aware in recent years, global temperatures have been on the rise and have been doing so at a potentially irreversible pace. Understanding the effect that these changes will have around the world will help researchers and citizens alike take better measures against forthcoming climate change. With a plethora of satellites in the sky, one may wonder why we even need something like ICESpark in the first place. Well, that's precisely the problem. There's simply too much geospatial big data from satellites for modern computing infrastructure to handle efficiently. As a result of this, independent scientists and researchers are left with little choice but to comb through huge amounts of data to find the relevant information for their research. As mentioned in the previous slide, there are huge amounts of satellites orbiting the Earth right now, more than 4,000 in fact, with that number only rising. With satellites collecting new scans of the Earth, and specifically the polar regions every day, we can clearly feel the strain for software capable of handling all of that geospatial big data. Over the course of this summer, my research and work on ICESpark has primarily been focused on finding the intersections between the EU Copernicus Sentinel-2 and NASA's ICESat-2. Here we have a simple infographic about the Sentinel-2 satellite and one about ICESat-2 as well. Deciphering the meaning of all that satellite data we have access to is the key to understanding what we can do better in preparation for climate changes that will likely happen in the near and distant future. During this summer, I was focused on data pipelines, which entailed the procuring of raw satellite readings and imagery, processing that data, and then putting that data to work by finding spatiotemporal intersections with already existing data sets from other satellites. This summer, we started off with the retrieval of Sentinel-2 raw data. To do this, we used a Python crawler, which gave us all of these XML files. There was hundreds of them. And within them, there was the data we wanted, this multi-polygon coordinate point thing going on here, and a lot of extraneous code. Once we cleaned that up, we got something like this. All the data we wanted and nothing we didn't need. Using this data that we got, along with these orbit coordinates, we were able to find spatiotemporal intersections right here listed in this table. Using the ID associated with these coordinate points, you can go back to Copernicus's website and find spectral imaging for specific coordinates. Tomorrow's problems with today's technology. With an environment like ICESpark that is tailored for and capable of processing the geospatial big data that we're now encountering, we will be able to make more accurate predictions about the climate in the future. For pharmacies and policymakers, this could mean increased efficiency in water allocation intelligence, leading to more successful crop harvests, or it could mean earlier notice of key information that can save a season's crop from natural disasters. For researchers, understanding and observing the ice melt ponds in the Arctic can help better gauge the rate at which the ice caps are melting. The seemingly insignificant melt ponds actually alter the partitioning of solar radiation by decreasing the area of reflective surfaces, which causes an increase in absorption and transmission of heat, all of which speeding up the rate of ice melt. The development of ICESpark and its various geospatial big data tools will serve professionals across many geoscience disciplines in tackling some of the world's most pressing climate issues. Thank you very much for listening. Any questions?